this whole algorithm that I introduced last week, the cross-entropy method, the point of it was to help you do importance sampling. So importance sampling, you need to provide the proposal distribution for which is central to importance sampling, and cross-entropy gets closer and closer to the absolute best proposal distribution that you can use for importance sampling. So this is an example where just trying to calculate the probability that some standard normal is above the threshold 5, and cross-entropy looks within a family of distributions to find the best in that family. So this family was just looking at normal distributions, and it moves across iteration 1, 2, 3, 4, 5 over to here, and this tries to get very close to this pink line, which is the what I wrote as G star of X last time, which was the absolute optimal proposal distribution out of all distributions. So I showed you the algorithm. So theoretically, you could have picked that up and just implemented that. You could have written some code to do cross-entropy, given what you knew last week. But there was this one sort of magical step, which is this part here. I wanted to say where it came from, basically. Like, what is it doing, and how could you derive that? So I'll go back a step. So at the high level, just again a reminder, you choose some family of distributions you're searching inside. You choose some starting point, which is some starting distribution, and then you step closer, and you're trying to, given where you are now, vi minus 1, you want to get the next one, which is as close as possible to the G star optimal one. And so that as close as possible is what I'll be discussing. Oh, actually, I forgot that at the exact moment that I left you, we'd just gone through this worked example for exponential distributions. So we'd looked at the family of exponential distributions, parameterized by the mean, and we just plugged it into the formula, which in one dimension turned into this, took the logarithm of the density, took its derivative with respect to that parameter, and at the end of the day, we got this thing here. So I was going to write some code to see if this actually works. I'll show you how it works, I should say. Yes?
Could you quickly just re-explain the difference between cross-entropy and importance sampling? Because you say that the use of cross-entropy will tend to the result of importance sampling.
Yeah.
But I don't really understand how, because you talk about G star.
Yes, yes.
That G star in your previous example was with nu, which was changing in the time. Mm-hmm. We find G star with this nu because it was the minimum variance in your previous example last week.
So the G star is a theoretical thing that we use in the algorithm, but it's not a practical thing. We can't ever actually use importance sampling with the G star because of the fact that to get that distribution, you need to know the probability that you're trying to estimate before you can use it. So what's happening here is so the cross-entropy method, it will just give you a sequence of distribution functions. So it draws this graph here. So you give it this curve, and it'll give you a better curve. And it just keeps giving you more and more distributions. But in a sense, that doesn't solve your problem. Your problem is, what is the probability of this rare event? And you're just using cross-entropy as a way to get prepared to solve that problem. And so cross-entropy will give you a distribution, and then you can take it and use importance sampling from there. And that is actually sampling from this distribution, the proposal distribution, counting how many times the rare event happens with those samples, weighting it by the likelihood ratio and taking the sample mean. So it's sort of separate. It's the last step, as you might want to say.
So cross-entropy just gives the G star. It
doesn't give you G star. It gets you close to G star. Yeah. So it'll give you the best you can do inside the family. You restrict it to some family, and it'll get as close as possible to G star in that family. And then from there, you just use normal importance sampling. Okay, so we've got some. Because no one here seems to particularly enjoy Python, I've been trying to figure out how this stuff would work in R. I did your quiz on the weekend in R, and it took me way longer than I thought it would. So, sorry if it took you guys a long time. It wasn't meant to be so hard. Anyway, so using this specific example for probability z is greater than 5, and we'll use these exponential family. So we'll start off. I'll make it bigger for now. Set gamma to be 5. We'll set the maximum number of iterations we want to do for the cross entropy to be some large number. In this case, it'll never get that far, but it's just something safe to do. We want to say how many Monte Carlo replicates to take. So 1,000,000 is a good enough number for a one-dimensional problem. And then set this row to be the fraction of the best performing ones that we take to perform to fit the distribution for the next iteration. So I'll implement this for loop on the left for the iteration I in 1 to max iterations. And then simulate from the distribution. Sorry, I should have put in our starting point here. So we can just start off with v equals 1. Just start off with a standard exponential as our first guess. And then take, so how do we simulate these? In R, that's the Rx function. You say how many you want, and then you put in here the shape, which is, our v is actually the mean, so you go 1 divided by v to get that. And then to get the quantile, thankfully there's some function called quantile. Say I want the 1 minus rho quantile of this sample quantile I should say, and that's going to be our intermediate threshold gamma I. So just going through line by line, translating it into R. So and then we hit our condition to say, are we going to finish iterating? Have we finished the iterations? And that happens when your intermediate level gets greater than or equal to your target level. And then now comes the hard part. How do you iterate from one proposal to the next? And that's this kind of this thing here. So we'll break it up. We can just do the indicators by themselves. Which x's are greater than gamma I? So that'll be a vector of true or false. We have the original density divided by the new density. So what are these things? The original density is the likelihood ratio numerator. This thing is a normal distribution. The thing on the bottom is where we actually sampled it from. And that's a density of the exponential distribution. And the total likelihood ratio is just these guys together. And so we can do this update in one go. So the numerator here is the indicators times this thing here is the likelihood ratios times the actual value of the sample x's, and then we're taking the sum of those things, because that's just a vector. And then the bottom is almost the same. We divide that through by the same thing, except there's no x's on the bottom. Okay, so that's the cross-entropy part of the thing done, and now the final step is to actually use this beautiful proposal distribution to do some estimation. So in that case, we can copy some of this code again, actually.
It's indicator.
Sorry?
Indicator.
So there's a typo somewhere? Which?
In the last time.
Indicator. Yes, indicator. Good spotted. Okay, so we simulate from the distribution that we found. We take this part is just identical. Ugh. Let me just put some of this on one line. So instead of comparing against an intermediate level, we compare against the gamma that we actually care about. These two steps don't change, likelihood ratio doesn't change. And then the estimate, we can print it out, is the average over these indicators multiplied by the likelihood ratios. Now, what's the probability that that would actually work first time? Yeah, I'm spelling this wrong every time. Oh, that didn't help. Voila. So this is our estimate. Now, is it right? No, it's 2.8 by 10 to the minus 7. Well, we could say all these rare events are approximately 0, but you won't get high marks on the exam.
It's not the R, it's the approximation.
Yes, exactly. And so in this case, we know the actual value of the probability that a normal distribution is greater than 5. That's 1 minus the probability is less than 5. And yeah, so we're pretty close with this. Or if you're... Another way to look at it is to... You can see what the V's are doing at each iteration. Nope. Oh well. It just uses one iteration. It goes from 1 up to 2.6 and then it's solved. Okay. So, what is actually happening? So, the distance that it's using, when I say it iterates and it takes a distribution and then it chooses another one which is closer to G star, the closer to needs to be measured somehow. So the way you measure this distance between the two distributions, in this case, is going to be this Kullback-Leibler divergence, which is what I've got on the right here, KL. So you pass in two different densities, and it's this defined to be this integral of f log and then the ratio of the two. So this CE, I'll explain on the next slide what's going on. This is some other thing called cross-entropy. And it's, if you look at it, it's almost the same definition. So how can we motivate using this bizarre looking integral as a distance between two distributions? Well, if you plug in the same density twice, you get back 0. So that's nice. The distance between x and x should always be 0. That's purely because you get the log of 1 in expectation, which is 0. And also, it's always positive. So that's actually takes a couple of steps to show. So the KL between f and g is an expectation. So expected value of f of x on g of x when the x comes from the f distribution. And so using, I forgot a big log in here, logarithm of this thing. Using the fact that you can switch the what's inside in the logarithm, just using some log rule, you can say this is the expectation under f of negative log g of x on f of x. Okay, and then why would you do that? Because the function, if you look at the function psi x equals negative log of x, that is, well, log goes up like that, so what would negative log look like? Something like that. So that's a convex function. And why do I care? There's this thing called Jensen's inequality that can be used for that. This is the actual inequality here, which works for any convex function. This was very popular in my PhD university because Jensen is Danish and my PhD was in Denmark. And they were always very proud of Danish mathematicians. So I'll follow that along and point that out. So what does it mean in this case? So we can say the expected value of the log is now like the log of the expected value. Well, it's not equal to that, but it's greater than that. So minus log of the expected value of g of x on f of x. This is all with respect to f. So this can simplify. So the minus the log, this expectation is really the integral over g of little x on f of little x multiplied by f of little x dx. And so the f's cancel out. You're left with integrating over g, which is just a probability density. So integrating over the whole real line of this thing, that's just going to be, it's going to add up to 1 equals minus log of 1 equals 0. So that's a long way to say that this bizarre looking thing, Kullback-Leibler, is always positive, and it is minimized at the value of 0 when you put in the same thing twice. So it is kind of like a distance. I'd point out, though, it's not actually a distance. The real name of it is divergence, because a distance, for something to be a distance, you have to say the distance between A and B is the same as the distance between B and A. It has to be symmetric, and this thing isn't. So if you look at, calculate the values for some f and g and then just swap them around, you'll get another number as the answer for the other way. So it is kind of a distance, but not if you told some pure mathematician, you'd get into a fight. So what is perhaps more useful to look at is instead this related definition, the cross-entropy. So this is where we get the name cross-entropy method. This is used in, if you guys do any machine learning and you do like classification, for example, problems, the loss that you minimize at the end of your problem is usually the cross-entropy loss between the categories that the things should be and the categories you expect them to be. So this cross-entropy thing is also a way to measure the distance between distributions. And in this specific case, for our problem, they actually tend to be the same thing. So if we have this problem where we're looking at the distance between f and g, but f is not changing, that's just some constant distribution, and we're moving g to be as close as possible to f, then that is, this should be the argument g that does that, argmin. That's argmin over all possible g's of KL. So we can use the other fact that log of f on g equals log of f minus log of g. And so we get integral f of x log f of x dx, subtract integral f of x log g of x dx. And so if we're changing g in this situation, this first term here, f log f, isn't changing at all. So if we're looking for the thing that minimizes this value, it's the same as looking at the thing that just minimizes the second value. So if we cross out, if we just ignore that first term and say that's just argmin over the g's of minus integral f of x log g of x dx, well, that's actually this thing over here, the same as minimizing the cross-entropy method. Oh, sorry, the cross-entropy between f and g. So in a sense, for our case, they're both interchangeable definitions. And unless you really like pronouncing bizarre European names like Kullback-Leibler, then just stick to cross-entropy. Otherwise, oh yeah, so I just pointed out here that with KL, if you put in the same thing twice, you get back 0, so it's kind of like an intuitive distance. But with cross-entropy, you put in f of f, you actually get back the entropy of f, which is just a fun fact. So okay, so this is our C here, and then during the C iterations, we try to get as close as possible to G star, given where we are, and that thing is, now I'll skip a step, like maximizing the indicator that our event actually happens. Times the distribution of the actual variable that we care about, times log of the density inside our parametric family dx. And so actually this is here in a nicer format. And effectively, you get that the best thing that you want to do, given the previous iteration of CE, to get the new one, is you want to get the thing that maximizes over all possible parameters v, this thing here, except we'll throw in, multiply it by 1. So the density of the previous iteration by itself, vi minus 1. Yep. My handwriting's getting worse every day. And I hope I put that on the next slide. Yeah, so this is what I was trying to write. So given the previous one, you choose your next parameter is the thing that maximizes indicator likelihood ratio logarithm. So this should look extremely similar now to what was in the formula, the recipe earlier on. Except the only thing missing is that we need to do what we did last week, which is this stochastic counterpart trick. So instead of maximizing an expectation, you sample from that distribution, and then you fix those things, those values, and maximize over like a Monte Carlo version of the optimal objective value. So here, if you sample from f given vi minus 1, in that case you do the summation of r equals 1 to capital R, and then basically the same thing here where all your x's are replaced by the actual sample. fxr xr given vi minus 1 log fxr and so on. Whew. And then the only thing missing between what was in the formula, the recipe that I gave at the beginning for what the cross-entropy method is and this is that instead of putting in the final value of gamma that you're trying to find which is the threshold that you care about for your rare event, you put in that quantile, the gamma I, which is like the 90% quantile of your x's. And that's just to make sure that these indicators aren't all zero. Because this is an approximation when instead of maximizing an expectation, if you instead maximize this sample thing, this stochastic counterpart, that's just some approximation, and it can go wildly wrong when these indicators are all zero. The whole thing just falls apart. So anyway, that's all I wanted to say about that detail. So why did I call this like a weighted maximum likelihood estimate? So if we were to look at just the normal problem of having some data, x1, x2 up to x capital R, and we wanted to fit it to some distribution f with parameter v, you would maximize the joint likelihood. So that's what this first term here is. Find the v star out of all possible v's that maximizes the probability, the product of the individual densities. And that thing is the same as maximizing the logarithm of the joint. So maximizing the log likelihood. So imagine instead of this product here, you just put a log around the whole thing. Well, then that log of a product turns into a sum of the logs of the individual values. So that's very standard statistics. And then the only thing, if you wanted to say, if you wanted to give more weight to some than others, if you were to add a weighting term inside here, multiplied by the log, then you would have weighted maximum likelihood, and that's exactly what the formula for cross-entropy gives you. If you can look at it in this format. So this is what the cross-entropy is doing at that stage. And if you pull out this part here, you can see that is the weight. But otherwise, you're basically just doing maximum likelihood over the elite samples that you've chosen. Okay, on to something far more interesting. So one reason I wanted to show you this algorithm, the cross-entropy, is it's really useful for rare events, but it's also really useful in a totally different scenario, which is just optimizing functions. And it's a really cool algorithm for that. So this is absolutely nothing to do with rare events, the next few minutes, but I think it's life skills. You might enjoy it. So say you have this function s of x can be unidimensional, but you can put in a vector here, x, And you want to find which is the x which gives you the largest value over that function. So it's very standard optimization. So the cross-entropy way of doing that would be to turn it into a sequence of distributions. So you start off with some distribution, V0. You sample from that distribution, and then you evaluate the objective function at each of those samples. And then you look at, you collect together this elite set, which is you've thrown down points randomly, and then you've looked at how does the objective function behave in that area. You take the ones that have the highest objective values, objective function values, and then you fit a distribution to those things, to those elite samples. And then you just repeat. There's nothing special. You just keep doing this, and your distribution should converge on the area which maximizes the function. Okay, so let's do this for this function that I've got here. So in Python land, this function s of x, you have to use the numpy command np.x minus x take 2 squared. This is literally the only point which R is better than Python. We can't just use the up arrow in Python, but otherwise Python is better in every single way. And then, so this is the first term plus np.x minus x plus 2 squared. And then we'll evaluate that over a grid of x's. We just want to look at that. That's a bad reaction. I've started writing this disgusting arrow instead of the equals sign. Anyway, that will make a grid which is just a linear grid between, say, -5 and 5 with a bunch of points. It doesn't matter how many there are. And then we'll plot those x points and the value of s and those x points. And so, voila, this is the thing we'll be trying to maximize. It's very, very simple, just a mixture of two normal densities, to be honest. So, how do we do that? Oh, what's happened here? So, we start off, what we'll do is, we'll choose the normal distribution, the family of distributions to search within to be normal. So we'll start off with mu equals 0 and a large sigma value. Sigma equals 20. We'll take R to be, we'll sample 50 points at each iteration, and rho will be 0.1, meaning that we'll take the top 10% performers to create the elite set. And then I'll just set the seed for the random number generator so that this plot is the same every time we do this. Okay, step 1, we just sample random variables. So from the normal distribution with that mean and standard deviation, say I want capital R of them. So let's just plot them for now to see where they fell. So we'll make the x grid between -5 and or if the smallest value of the x's is less than that, then we'll plot it back even lower, or plot up to 5. Similarly, if the largest value we sampled is larger, then we'll keep the plot going up to there. 500 points over that grid. Plot the x's, the objective function over that grid, and then we'll throw down a scatter plot on top of that of the actual values that we found, that we sampled, and the objective function at those points. So, in iteration 1 of our optimization algorithm, we threw down these points here in blue. Most of them were in terrible locations. A couple of them landed on the peaks. So the idea is cross-entropy will pick up those guys and then fit a new normal distribution to the ones that are on the peaks here. So high up. So what does that look like? So we take that intermediate level gamma I to be the quantile of the objective values, where we take the top 1 minus row quantile. So, and the elite values are then those x's which have an objective function which is above that threshold. So let's copy some code from back here. Plot the function, plot the scatter plot, and then make sure we can see which elites we've taken. Yep, that didn't work. That's better. So we found some threshold gamma I. Maybe I'll just throw down that in the plot as well. I'll just put a line across the plot which shows the threshold that we've found, so the gamma I. Okay, so what we've done is we've sampled these guys here in the first iteration. We found out what the objective function is at those points, and then we found the 90% threshold, in which 90% of the samples are below that threshold. So that's this gold line here. And so all the points that landed above that, the ones that are now in red, are the elite samples. And then what we can do is fit a normal distribution just to those samples and repeat the process. So before, when we sample, we use mu and sigma. So we'll replace that value with the sample mean of the elites, and similarly the standard deviation of the elites. Okay, I won't go through write the code for every iteration, but iteration 2, then we've sort of zoomed in on the area which has the peaks inside it, and we've sampled these plots here, these points. Yep. Okay, and then from those points there, you again get the new threshold, which is way higher, and you pick the top 10% elite sample from there, and then you can see that the points are already at the global maximum for the function. It's basically already solved the problem. And the next time you sample, you're sampling from this normal distribution, which is just on that area with a tiny variance, and it's more or less converged to this optimal value. Yes?
What I don't understand is that you need the function to get the target function to get the 10% point. To put the point on the curve, you need to add the target function. So I don't know why is it optimization if you already have the target function.
Well, it's every optimization, numerical optimization algorithm, you need to be able to evaluate the objective function. So they all rely on that, but most of them, you need more information than that. They actually require that you can calculate the derivative of the target function and the second derivative and those kind of things. So in a sense, this is actually requiring less from us than most algorithms. We just need to be able to say, for this point, is it a good point or a bad point, basically. Just say, is it a high S or a low S? But even, there are still lots of problems where you can write down the function of the thing you want to maximize, but you still can't.
So this function isn't just an example because you can derive it.
Exactly,
but
yeah.
If you have more complex function,
Exactly.
use it.
And one such function is this divergence function. And this is what it looks like. So this is it's defined on, well, this one is on 2 dimensions, and it's not really a function that came from some useful part of science. It was a function that some guy came up with to kill numerical optimization. Because most standard numerical optimization is you start at some point, and then you do this thing called like hill climbing. You basically say, imagine you're on one of these peaks, say there, and you say, well, in which direction is the steepest descent from where I am, and then follow that direction down to try to find the minimum value of a function. But this thing has hundreds of these little valleys that's designed to trap those kind of algorithms. So that most of the old style numerical optimization algorithms would never find the minimum value, which is actually right in the middle at 0, 0. It would just stuck in one of the local minima. And so cross-entropy applied to this. This is an example that you guys will be replicating in your quiz. What you can do, I should say, is start with bivariate normal distributions and just throw down some points. And so this is an animation on the left here of the points that are being thrown down at different iterations for various bivariate normal distributions. And they've been colored differently, whether they are the elite ones or just all the other points that didn't make it into the elite set. Beside it, you can see the actual distributions that were used to sample these things at each iteration. And you can see that the distributions are closing in on the center 0, 0, which is the global minimum value. Even though it's probably hard to tell, but at iteration 1, the first samples were a long way from 0, 0. They're at like 100, 100, 150, 150. But because the variance was quite large, it just threw down samples in all directions, and it found ones that were very far away that were much better, and it could find which direction it needed to move in. And so if you kept track of every time you threw down some samples and you calculate the objective function at each of those points, if you kept track of this over each iteration and say what is the very smallest or the very best objective value over each iteration, this is what this plot looks like. So the x-axis is not the number of iterations of the cross-entropy method. The y-axis is the objective value. And so you can see this is on a log scale, so that your function is getting optimized at some exponential rate, basically. So, okay. And this stuff, oh no, I guess that's still a few more minutes. So some things that I probably skipped over when talking about cross-entropy last time is that maybe it's not clear which family of distributions to be searching inside of. And then the other hidden assumption is for whatever family that you have, you need to be able to simulate it from that family. And that's where exponential tilting can help out with at least the first problem. So when you take any density f, you can create a whole sequence of new densities from it, the exponentially tilted densities. So the way I'll call the exponentially tilted one f of x given theta. Theta is the tilting parameter, and it's defined by e to the theta x multiplied by the original density. And then for this thing to become a distribution, you need to divide through by the normalizing constant, which happens to be the moment generating function evaluated at theta. For this one, the gamma distribution with this specific parameterization, e to the xr to the minus 1, etc., etc. The moment generating function, I couldn't be bothered going through the math, but you can figure it out that it's 1 minus mt to the power of minus r. And so one thing to note here is that this is not going to always exist. I guess if I write it differently, it might emphasize this. 1 on 1 minus mt to the positive r. So this thing can blow up easily if you're doing anything 1 divided by 0, basically. So when this happens, that's when 1 minus mt equals 0. And so the critical value of that is t equals 1 on m. So effectively, you need to have this function is well defined for t, which is less than that threshold, 1 on m. And this is a common thing for moment generating functions for most distributions. They don't work, as it were, over the whole range of possible values. It's usually they're happy to work if you put in a negative value. Every distribution you can put in a negative thing. That's usually defined as the Laplace transform. But for the positive section, you can either go a little bit into the positive realm or not at all for some distributions. So what does this look like? So just for some gamma distribution, r equals 2m equals m, if you tilt it by a little bit, theta equals a half, then that scaling factor that we just looked at is 1 minus m theta to the power of minus r. If we plot this over just some grid, 0 to 10, then we can show what the original PDF was at these points, and then the tilted PDF, which is exponential theta times x times the original density divided through by that moment generating function evaluated at theta. So we can throw these down together. Put on a legend so we can tell them apart. So here we have the original gamma PDF, and we've tilted it by theta equals half. And what that's done is it's pushed the whole distribution to the right. It's made larger values more likely. So if we push it even further, 0.75, you can see it's the more you increase that, the more you push it to the right. What other ones are there? If you tilt it by 0, nothing happens. You get back what you started with. So the family includes that, and you can actually go backwards. You can say tilt it with a negative value, and it makes smaller values more likely. But one thing that'll happen is, say, if I try to tilt it by 2, you'll see the whole plot just crashes, because now you're doing e to the 2 times x times something else, and that something else can't normalize it, so the thing just goes off to infinity. It's no longer a distribution function.